Crash Course 2 Periodic Table Classification. This is the second installment, and I am going in order of how the New York State Regents gives out its questions in the multiple choice section. So let's get started. So we're talking about the periodic table. We cannot help but talk about who was the first to get credit for classifying it, and it's Dmitry Mendeleev. This Russian scientist, and yes, he looks like a party animal, this Russian scientist was first to get credit for putting together a comprehensive table that put atoms in order of their atomic mass. But what you have to know is that he was the one responsible for this table, and you should know that the current periodic table is based on atomic number. How do we know this? If you look at the atomic number, okay, it goes from 1 to 2 to 3. Of course, it goes in order of the number of protons, and it doesn't skip around. Unlike atomic mass. Atomic mass certainly does not go in order, and there's plenty of examples of that. Okay, let's look carefully right here. And Dmitry Mendeleev's table, okay, is cobalt, nickel. Cobalt is 58.9, nickel is 58.6. So you can clearly see right here that the table does not go in order of atomic mass. Mostly it does. In fact, when they discovered protons much later after Dmitry's table, they had to actually switch a couple of these because these had very similar properties. But Dmitry's table is based in the idea that chemicals had periodic properties. These properties, okay, were something that he could see on the macroscopic scale. Their chemical reactivity, their ability to bond with other things. These are things that they knew of the elements of the time. There were about 60 or so elements he was working with at the time, and he saw that the properties repeated themselves. We now know that those properties repeat themselves because these atoms have the same number of valence electrons. Very important. Okay, so if you're in the same family of elements, same group, you have the same number of valence electrons. Now, he didn't know anything about electrons, didn't know anything about electron configuration, stability, just saw that these properties periodically repeated, because as he went across, there was an increase in chemical reactivity, and then it stopped. And then the reactivity increased again, and then it slowed down. And then so these patterns kept increasing, okay, and decreasing. Something about this table. Okay, so any case, what made his table really amazing was that he was able to actually predict elements that, when found, would go from them, would go in between what they knew. Okay, for instance, germanium, okay, was an element he predicted would fit between gallium and arsenic. He knew that there was a mass here of 67 or 70-ish or so, and he knew arsenic was much heavier, but he knew that he was skipping some of these other elements that had the same periodic properties. And my friend, he figured out that if there was an element between these two masses, then it would fit, it would have the properties of silicon and carbon. And he did that for several atoms before and after his death. Okay, so that really gave a lot of credence to what he was doing. But what were these periodic properties? Well, there's 3 of them. Okay, one is atomic radii. That means that the radius of an atom from the nucleus to the outermost electron, okay, if you measure that radius, there's something about the size of an atom, okay, that periodically repeats itself, okay, and lends itself to the properties. That was one. Now, atomic radii, okay, really drives the other 2. The other one is electronegativity, which we should all know is the attraction for electrons. And if you think about it, if you're a small atom, that must mean that your electrons are pulled in closer to the nucleus, okay, and therefore you must have a great attraction for electrons. Now, really, electronegativity is the attraction for other atoms' electrons, okay? That's why noble gases, which tend to be the smallest atoms, tend to have no attraction for other people's electrons because they're stable. Okay, then we have ionization energy. Ion, look at that word, ionization energy. Now, this trend that repeated itself like the other 2 was the measure of how much energy it took to grab or pull an electron away. So the energy to make a positive ion, or the energy to pull an electron away. So if you're a small atom, okay, look at a big atom. Here's a big atom, positive nucleus. Here's an electron. Here's a small atom that really attracts its electrons. Well, it makes sense that the smaller radii, okay, are going to have a high electronegativity or attraction because, well, they're pulling that electron in because they have some kind of nucleus that really can pull and has a really high ability to attract these electrons. So electronegativity is high. Now, if you're attracting your electrons really high, it makes sense it takes a lot of energy to pull electrons away, so your ionization energy is also high. If you're a large radii, okay, it makes sense that you have a poor electronegativity. Why? Because that electron is so far away from the nucleus, you don't really attract it. And of course, you would have a low amount of ionization energy because it takes a lot less energy to pull this electron away because the nucleus doesn't attract it that well. That's why it's large. So my friends in chemistry, these things repeat themselves over and over on the periodic table, and they go based on, as you could probably see here, atomic radii. As the atoms get bigger, okay, let me just repeat, let's do that a different way. As the atoms get smaller, okay, their ability to attract electrons increases. They have a greater grip on their electrons, so it takes a greater amount of energy to pull them away, and of course their radii is smaller. What we're discussing and describing are the properties of nonmetals. A nonmetal, okay, really is defined by these three trends. And what we're describing here with a large radii are metals. Metals are defined, okay, by these parameters. Okay, so if you look at the periodic table, we're going to see how metals become nonmetals and vice versa. So here we have a beautiful chart that Flynn gave me, and look at their radius. Let's look at the second periodic table, the second principal energy level, I should say. Look how the radius gets smaller as they go across. If you look at this row, okay, you can see that, wow, we go across, we're adding more protons in the same energy shell, so we're attracting electrons more. So these guys have tremendous amount of attraction over here, and here they start out big. So look at the trend. As you go across the periodic table, the radius gets smaller because we're adding more protons, and that we say the nuclear charge, the charge in the nucleus, is increasing. So we're becoming more like what? Nonmetals. And over here, the radius are larger, which means we hold on to electrons loosely. We are metals. And you've already learned, my friends in chemistry, the ones that are transitioning between the metals and the nonmetals that aren't as reactive, and you've guessed it, okay, are your transitional metals. They're not quite as big as these reactive metals, and they're not quite as small as these nonmetals. So as you go across and up on the periodic table, you get smaller. Okay, you become more like a nonmetal. That's why the most reactive nonmetal is fluorine. These guys are the smallest, but these are the noble gases. They're not reactive in this column here. Okay, the most active or reactive metals are here. And what is that activity? Metals lose electrons because they're so big. They hold on to them so loosely. Nonmetals gain electrons. Hey, we learned about redox. Gaining electrons is called what? You guessed it, reduction. Nonmetals like to gain electrons. The proof is they become negatively charged. Metals lose electrons. What do we call that? We call that oxidation. Oxidation. Okay, Leo the lion, losing electrons. Gur, gaining electrons. See, most of the periodic table, my friend, is metals. They're big, they lose electrons. And where's the proof in that? Let me show you. Now, before we do that, let's think about this for a second. You should know why, okay, why the atoms get smaller as we go across. It's because you're adding protons in the same energy level. Now, with that, You may think, well, why do they get bigger as I go down? Because I have more, certainly I have more protons as I go down the periodic table. Well, here's the reason for that. If you have lithium has 2 energy levels with electrons, okay? And sodium has 3. So if you think with me for a second, sodium has an extra layer of electrons that shield the nucleus. We call it the shielding effect, okay, in New York State Regents. So as we go down, there's more layers of electrons. Let me show you what I mean. Okay, lithium is 2-1, 3 electrons. Sodium, okay, is 2-8, sorry, 1, okay, and of course 11, atomic number. So if you think with me for a second, here's a nucleus, and if we just use a Bohr diagram, I know electrons don't go in circular orbits, but we're just going to use that as a reference. We have 2 electrons close to the nucleus, so does sodium. Then in another orbit, or at least shell, we'll say, this guy has 1 electron. Well, sodium has the 2, but it also has 8 electrons. And these 8 electrons, okay, I think I got 8 there. All right, one more. Shield the nucleus because they have an extra electron that's further away. And therefore, these electrons make it hard for this nucleus to attract it. So they get bigger. It's called the shielding effect. Remember the kindergartner? Kindergartner got my wallet the other day. I was in Tanger. I was shopping. Okay, so he got my wallet, and I tried to go get it, and he ran, but all of his kindergartner friends jumped in my way, and I couldn't get to that kindergarten. They shielded me. So the reason why you get bigger as you go down is because of the extra shells of electrons. Okay, I know, again, we're using Bohr diagrams, and we can make that analogy fine. Okay, so any case, we're now defining metals and nonmetals. Let's go back to the periodic table. And as we talked about, my friends in chemistry, metals are the most abundant of all of the elements. Above the staircase, we have our nonmetals, the smaller atoms, who are smaller, attract the electrons, take a lot more energy, called ionization energy, to take away. And of course, these atoms are your metals. And metals are big. And the case that I want to make here is find me an oxidation number, okay, that is not positive. They're all positive. Look at these oxidation numbers. Upper right, these are all the charges these metals love to become. Metals don't become negative. And nonmetals, you'll see their top oxidation state, okay, is negative. Okay, apparently the cops want to talk to me. Just kidding. I don't know, I got some sirens in the background. Okay, maybe I got to cut this short. Got to take off. Just kidding. Any case, trying to focus, apparently. Okay, so let's look again. Big metals versus big atoms, the metals versus small atoms. Okay, now before we get involved here, let's define who are atoms who have properties of both. Boron, okay, silicon, arsenic, tellurium, germanium, antimony. These elements, okay, have both properties of the bigs and the smalls. The big atoms, metals; small atoms, the nonmetals. And they're called the semimetals or the metalloids. And you should know them, okay? And what are these properties? Okay, real quickly, metals, because they hold on to electrons loosely, their electrons are free to move. They're great conductors, okay? They are great conductors of heat and electricity. Nonmetals are terrible conductors of heat and electricity because they hold on electrons so tightly. The lack of motion that electrons can have, okay, makes them good insulators. Okay, metals are malleable and ductile. They can be shaped if you heat them for the most part because of the metallic bonding, that loosely held electron arrangement that all the nuclei can attract all the electrons, okay, like a sea of mobile electrons. The nonmetals, because they hold on electrons tightly, they're a little more OCD. They tend to break easily. They tend to get bothered and they shatter easily. And then, of course, they are brittle. Okay, I showed you dry ice is a brittle solid. And those are the major properties, okay, of these types of atoms. All right. All right. Now, Of course, metals tend to have a high melting point. Nonmetals tend to have a lower melting point. Think of your organic chemistry. I've always said think of butter, rubber, plastics, okay, leather. These things have low melting points. These things have high melting points because of their arrangement of electrons. All right. Now, something else to review here is the family of elements. Okay. Now, as I talked about before, if you're in a certain column, you have the same number of valence electrons, and therefore you have the same chemical reactivity. So, my friends in chemistry, these are called the alkali metals. All right, the alkali metals. These are called the alkaline earth metals. Alkaline earth. Okay, what's so special about them? Well, these guys are the most reactive metals. They're not found in nature unless they're already combined. These things will explode in water, and are only made in their pure form by electrolysis of a fused salt. Okay, then we have, okay, a bunch of other groups, but the ones we care about are these, group 17. These are the halogens. Okay, and of course we have our noble gases, group 18. All right, let me go to the other table for a second. Okay, so we got our alkali metals. Okay, we have our alkaline earth metals. These all are +2. These all are +1. I don't know. We have our halogens. I'm not sure if you like my color motif. And then we have the I don't know, the noble gases. Okay, those are the 4 family of elements. Of course, the noble gases have the least amount of chemical reactivity. The rest of these other 3 have very high chemical reactivity. The halogens are the most reactive nonmetals, and these guys are the most reactive metals. Now, kind of questions you'll see as I go across the periodic table, my non-metallic reactivity increases because I'm becoming more like a nonmetal, smaller. As I go this way, I become more like a metal. So my metallic reactivity increases. If I go down any column, my metallic properties increase because I'm getting bigger as I go down. As I go up any property, every group, my non-metallic properties increase because my radius gets smaller. A couple other things that you should know. Okay, the LL rule. Let's get some things out of here. Okay, you should know that all your gases at STP. Let's do that. Let me get a nice motif here for your viewing pleasures. Okay, so let's go to, let's do this one. So this is, how about I to choose this? Let's do a highlighter. That's not the color I wanted, but hey, here's 1L and here's NOFGL. These are all your gases in STP. Okay, NOFCl, sorry about that. And here is the other backwards L, called the LL rule. Here's all your gases. Okay, then we have 2 liquids, bromine and mercury at STP. Everybody else is a solid. Interesting to note, maybe not that interesting, the halogens actually have 3 different phases of matter. They have 2 gases, okay, a liquid, and a solid. And look at 15. We go from nitrogen to phosphorus to arsenic to antimony, bismuth. Bismuth is a metal. Arsenic's a nonmetal. These guys, arsenic is a metalloid in between. There's your nonmetals. Okay, and that essentially covers the periodic table. Okay, and now we're going to go on to classification of matter. Classify matter. We can break it down into homogeneous and heterogeneous type of matter. First and foremost, let's start with a mixture. A mixture is 2 or more substances in close proximity but not chemically bonded. They're put together physically and they're separated physically. So this is atom red and this is atom blue. Okay, we can see that this is a mixture. And for the most parts, it'll probably be heterogeneous. Okay, most mixtures are. Okay, no bonds between them, and they're basically haphazardly mixed. There's no evenness about them. So these are 2 different atoms mixed together. To separate them, we could separate them physically by plucking them out, or if they had some physical properties that differ amongst them. For instance, the red might have a different boiling point. Okay, therefore I can separate it by distillation. Distillation, okay, is a separatory technique. We separate them by physical properties, and you should know that boiling is a physical property because if you take H2O, let's say liquid, and go to H2O gas, Okay, the boiling point at STP is 100 degrees Celsius. If you notice, the chemical formula is not changing. So this leads me into physical and chemical properties. So all the phase changes, liquid to gas to solid, in this case ice, are all physical properties. And they're all physical properties because we're not changing the chemical formula. We're not breaking bonds, we're not creating new ones. We're just basically changing its arrangement, which is a physical change. So phase changes are not chemical. So we can separate a mixture based on its physical changes, okay, in its background. Okay? Thus a chemical change, okay, is one where you are breaking bonds, like hydrogen and oxygen gas can combine, break their individual bonds, and reform water. Notice we're creating a brand new substance from different substances. Therefore, it's a chemical change. How else can we separate things physically? Well, we can separate them by size using filter paper, right? You can filter out, let's say, big rocks from small rocks or precipitates from a solution using filter. And we've done that in a couple of different labs this year. So we can also separate from boiling off the compound and leaving behind the salt. Remember the lab where we had sodium carbonate? So you added some acid to it, and then we saw the bubbling, and then we burned off the water, and we just left the solid. So we can evaporate off the water and leave the salt behind. And there's another one that comes up, and that's chromatography. Chromatography is when you take some kind of mobile phase and a solid phase, and you would, let's say, spot a plate somehow, and you could see that these dots would go up at different amounts depending upon their ability to attract the liquid that's going up by capillary action, or if they want to stick with the solid phase. So we give elements or compounds a choice to either stick with the polar or nonpolar side, and based on their individual solubilities, which is a physical property, how well something dissolves, okay, breaks apart into a solvent, okay, we can separate something based on that. So those are the basic type of separatory, but they're all physical, and they're all for mixtures. Mixtures are nothing more than physical things put together but not chemically bonded. So that's very important. Now, of course, I showed you a heterogeneous mixture. A homogeneous mixture is a solution. That you should know. And a solution means dissolved. And if it's dissolved, we're going to write chemically aqueous. We know that that's a solution. And we also know that this is an electrolyte because when it's aqueous, this thing breaks apart into those ions. And those ions, if you remember, are surrounded by those molecule ion attractions. Remember water? Water is attract the negative end of that chloride molecule, and the negative end of the oxygen, okay, is going to attract the sodium end. So the positive end of the water attracts the negative. I call these famous boyfriend, famous girlfriend attractions. The negative part of water attracts the sodium ion, and the positive part of water attracts the chloride. Just like if two famous couples were to walk down the block, they would get probably rushed, and all the guys would surround the girl, all the girls surround the guy, and they'd be pulled away from each other if they were hand in hand. Maybe, maybe not. Who knows? So that's the basics there, okay, of your mixtures. The biggest example of mixtures that we have in this course are, again, our solutions, denoted by the aqueous. Okay, but if you're not sure, just think of, is it dissolved or not? If it's dissolved, it's a homogeneous mixture. If it's not, okay, it's a heterogeneous mixture. Don't forget, gases are also homogeneous mixtures, because I just ran into a pocket of no oxygen. That doesn't really happen, okay? So therefore, gases are considered to be solutions as well. Okay, so in any case, here we go with compounds and elements. An element, of course, is the group of the same type of atoms. Now, we know that atoms are the same by their proton number, but if I was to give you a picture diagram or a molecular model diagram, you should know that this is an element. And we're going to write black dots as one atom. So the same types of atoms as an element. But I also could bond them with themselves. Don't forget we have diatomic elements, right? Diatomic elements are your Hofbrinkels. At least that's how I call them. Hofbrinkels, Hofbrinkel. CLS, these guys love to bond with themselves, the Hofbrinkels. They're diatomic. This isn't one big molecule. I'm just showing you that these are the elements that love to bond with themselves. So if you see a diagram where the same atoms, okay, bonding with themselves, then you know that you have an element, group of the same type of atoms. So if I was to write Br2, that's an element. Just if I was to write neon, that's an element. And you know in redox, elements are electrically neutral. That's why you did that. Why? The protons equal electrons. Okay? Now, of course, this is not a mixture because it's the same thing, right? It's the same group of the same type of atoms. So this is not a mixture until I what? Add another set of atoms. So now I have a mixture of elements. Two different types of element. One is monoatomic, one is diatomic. And by the way, we cannot separate elements further in this course. Elements, okay, and very important, are the most simplest form of matter we deal with, so they cannot be separated further. So if I give you a choice or a classic Regents question that says, hey, which one cannot be simplified into anything further, you're looking for the element. A compound, okay, can be, because a compound is made of two or more atoms bonded together. For instance, sodium chloride, two different capitals, two different elements, and therefore that can be broken down by, you guessed it, a chemical change, because you're breaking bonds into the individual atoms. And of course, compounds break down into, eventually, the elements. Now, compounds by definition are the same what? Same molecules. And a molecule by New York State is two or more different atoms chemically combined. So water has at least two different what? Capital letters, so therefore this is a molecule, and a group of the water molecules is a compound. Okay, and that's essentially all we have. Now understand that compounds are separated and made chemically because they have to be bonded between the oxygens. Mixtures are made and separated physically. Okay, and that's the major difference. And that's essentially what you have for classification of matter. Again, these are review videos and not at all used for should not be used for initial learning. Okay, I have those videos below this one at my site if you want more instruction in more detail. Okay, hope that helped. Okay, one thing that I did forget now that I just ended the video was that transitional elements, if you remember, okay, are the ones transitioning into nonmetals, and these have a very famous property. They make complex ions in water, therefore they're responsible for the color solutions. So solutions that have color, like why our blood is red is because of the iron. Okay, we dealt with copper being that blue-green. Okay, maybe chromium, okay, another type of green. But in any case, these guys, well, I should really write the transitional metals are ones that are transitioning from metals to nonmetals, but I probably should correctly make them these. Okay, you have to have partially filled electrons in that D block, and I mean, we don't learn that Regents chemistry, just being accurate. So what they have is they make colored solutions, and they also have multiple oxidation state, like cobalt can be +2 and +3, nickel can be +2 and +3. Okay, vanadium +2, +3, +4, +5. So most of these have multiple oxidation states, and that's another property of these guys. Okay, and they're the best conductors of electricity and heat because they have the most electrons of the metals. The reactive metals definitely are conductors as well, but nowhere near the ability that these guys do. Sorry to forget that. Okay, I'm done.